So today I want to talk about linear functions, and this is the beginning of chapter 2 in your in the pre-calculus text, and hopefully most of this is going to be a review for you. But what we're going to do, starting with these next couple chapters, is we're going to march through a lot of the toolkit functions and look at them in a little bit more depth to see how to graph them, what their behavior is, and all sorts of things like that. So for probably the next 2 weeks we're going to be doing that. We're going to look at linear functions first. Now, a linear function is some type of function that perhaps has an initial value and then a value that's modified by a rate of change, and that rate of change is going to be constant, and that's similar to, let's say, if you're driving in your car and you're driving at a steady rate. That would be your distance would be a linear function of time. The rate of change that you would have is your speed. So if you're traveling steadily at 50 miles per hour for 2 hours and you start at mile 0, you're going to be at mile 100. So that's what we refer to as a linear function, because the rate of change doesn't change. Now, there's several ways to write a linear function, and oftentimes you'll see it a little differently than the equation that you normally see written as a line. And if you use different kinds of computer programs, like actually just use your a TI-83 calculator, or a lot of functions, or a lot of programs that'll give you functions, it'll list the terms in a slightly different order than you're used to, like f at x equals a0 plus a1x, and so a0 is the initial value and then a1 is that constant rate of change. Now, I'm not going to really talk about it in that form, but just be aware that very often you get it in this form. This is actually quite comparable to the usual equation of a line that you talk about, y equals mx plus b, and so these two are similar in the sense that f at x would be y, and that your slope is a1 and your intercept is a0. And I'll go over those concepts of slope and intercept in the first part of the lecture here. So the thing to remember, the difference between simply an equation and a function is that the equation just relates to variables. A function takes an independent variable and it creates a value that we call the dependent variable. So this is an equation of a line, and if we can look at this as a function, if we call x the independent variable, meaning the value that we choose, and then y is the dependent variable, which is the value that depends on what we've chosen for x. So it follows that form of a function where you give it an input in x and you get an output in y. So let's look at slopes and graphs of linear equations first, or linear functions. If we have just a graph, we call the change, or the slantedness of the line, its slope. And so the way we measure slope is that we look at whatever horizontal change we have, compare it to the vertical change. Now we want a number that represents what we think of as a slope, and so with a large change in y and a small change in x, we would have a fairly steep line. And so if we define the slope as the ratio between the change in y and the change in x, then we'll have a numeric value that actually corresponds to what we would think of with a steep slope. So let's call the slope m, and m is just the constant that we use to represent the slope. So if the slope is the change in y divided by the change in x, that translates into a formula as y2 minus y1 divided by x2 minus x1. So it's the rise over the run. Perhaps you've heard that phrase before. For some reason it's easy to remember, but I'm not exactly sure why, because nothing really says it shouldn't be run over rise, but the convention is that we put the rise over the run. Now, it doesn't matter which point we consider point 1 and point 2. If we change this around to y1 minus y2 over x1 minus x2, we'll get the same value because the top would be the negative version, the bottom would be the negative versions, and the 2 would cancel out to be positive. So the choice of which point you choose as the first and the second point is purely arbitrary, and you just perhaps will pick it because it's the easier way to compute something, so you don't have to cancel double negatives and things of that sort. So if I take a point, or let's say take a line, now this one doesn't go through the origin, but if I take 2 points, I can calculate the slope just by taking the difference between the 2 y values, 4 minus 2, and then 5 and negative 1. Now notice I put those values in parentheses. One of the things that I think we make a lot of mistakes with inadvertently, it's not that you don't understand these things, but when we're taking differences, and let's say this 2 was a negative 2, you don't have to worry about doing all the computation in your head necessarily. Just lay it out with a minus a negative value, and so once you have it written down, then it becomes a little easier and more reliable to do. You don't have to do it. I just find that for me, it's very often convenient to write parentheses, first kind of write the framework of it, then drop in the numbers. So this particular one, 4 minus 2 is 2, 5 minus 1 is 4, and so that reduces to 1/2. Another example, let's say we have this line here, and so we're going to choose 2 points and call those points out as 2 and negative 4, and then negative 2 and 6, and then compute the slope. And here again you can see what I mean by using parentheses to keep your negative straight, and then once you have that, it's easy to simplify then, and so we get a slope of negative 5/2. Now you see that this thing is sloping from the upper left to the lower right. That means that it's a negative slope, so it's going down if you want to think of increasing x. And then the steeper we get here, the higher the numerical value that we have here. So if we look at the absolute value of this, as this line gets more and more sloped down, this number gets higher and higher, so the negative number becomes smaller and smaller. So it's just nice to have numbers that correspond intuitively to what you would think if you just made some conventions about what's up and down, what's increasing and decreasing. Now there's several forms of the line. There's 3 forms that we're going to talk about today. The one that is perhaps the most useful is the slope-intercept form. And that's just basically your y equals mx plus b. So if this would be a function, it would be f at x equals mx plus b. So the m, of course, is the slope. The b is the y-intercept. And so to kind of relate it back to that a0 and a1 business, when x is 0, the y value is b, and so that it crosses over the y-axis at the value b. So this is a fairly useful form in that it tells you right away what your initial value is when x is 0, and it also makes it convenient to graph in most cases. So when we think about what the slopes are, we can look at the signs of m and see what's really going on. So if m is a positive value, we have a positive slope. That means y increases with x increases. When m equals 0, that means there's no slope, so y does not change. So if m is 0, you can see y equals b, and so your formula for a horizontal line is just y equals some number. When m is negative, that means that y decreases as x increases. Okay, and then if m is undefined, what we have there is a vertical line. So let me draw a couple pictures here of the horizontal and vertical lines. And so if we have on an XY chart graph, and let's say we have a horizontal line like this, if we take, let's say, these 2 points, where this is, say, 1 and 3, so these points here would correspond to 1, 4, and this would correspond to 3, 4. If we calculate our slope, we have 4 minus 4 over 3 minus 1 is 0 over 2, so our slope is 0. So we would write this equation simply as y equals 4. Now, if we have the other case where we're looking at a vertical line, let's say here's my vertical line. And so I not only have this point that's 1, 4, but let's say I also have this point which corresponds to 1, negative 4. If I calculate the slope of my vertical line, that would be 4 minus a negative 4 over 1 minus 1. And so here we have 8 over 0. And so there's no defined slope here because division by 0 is not defined. So the equation of this line then is only x equals 1. Okay, so here we have what are just kind of values assigned, but when you consider them in the context of both x and y, we have a horizontal line here and a vertical line there. Okay, so let me run through this example. If we have y equals 2x plus 1, our slope is 2, the y-intercept is 1, and so to graph this thing is fairly straightforward. We can make our scale, and our y-intercept is the initial value, so that's where it crosses the y-intercept. Since the slope is positive, you're going to expect it to go from the lower left to the upper right. And so what we can do is count off what our slope is. So we go, it rises 2, it goes, the run is 1, so it goes over 1, up 2, and then we can do that for several points, in both directions actually. And basically, we note that really only 2 points are necessary for a line. And so when you are, depending on what kind of paper you're using or how carefully you're making your graph, if you just have these first 2 points and you take your straight edge, you can draw your line. You don't need multiple points. And so long as it's in this form, that's all you need, are 2 points. Now, the other thing that you can do to aid yourself in graphing is that you can make the slope into a different ratio, like instead of 2 over 1, the slope of 2, 4 over 2 is a different way to represent 2. And so what you can do then is just go over 2 and up 4, and then you have 2 points that are more widely spaced, and that will facilitate a more accurate line, because with 2 wider spaced lines, it'll be easier to draw a line that's accurate over the whole graph. Okay, so let's look a little bit more about slopes here. If we have 2 lines here, I'm going to draw 2. And they have different intercepts, but the same slope, this will be a parallel line. Okay, so notice that if I count off my slope, I'm going up 3 and over 4, or here I'm going over 4 and up 3, that's the same thing. I have the equation of the line is the rise over the run will give me a slope of 3/4, and the intercept is 1, so this equation is y equals 3/4 plus x, or 3/4 x plus 1. This one, same slope, rise over run is 3/4, but the intercept is -1. So with these parallel lines, the slopes are the same, and in fact, any line that has the same slope will be parallel. And so that's an easy thing to remember. Now, let's kind of prove to ourselves that these will never intersect, because obviously you can't make a proof graphically, because that's only as accurate as I draw it. But if I know that my intersection is going to happen when both x's are the same and both y's are the same for both of these, we know we have a point of intersection. And so if I just make this y1 and x1 for the first equation, y2 and x2 for the second equation, if the two y's are equal to each other, I can set these two equations equal to each other, and I'm going to expect that I get some solution of x that will tell me where the point of intersection is. But if I subtract 3/4 x from both sides, I'll get 1 equals -1. So there's an analytic proof that says there is no point of intersection. If you have the same slope with different intercepts, there's no way that you're ever going to intersect. Okay, so the big takeaway here is that, of course, parallel lines by definition do not intersect, and that the equations of the lines, the slopes will always be equal. Okay, now let's talk about perpendicular lines, and most texts don't really justify why perpendicular lines have the slopes they have, and so I want to kind of walk through a visual exercise in convincing you why the slopes are related the way they are. Imagine I have this rectangle, and it can have any dimensions, but I just chose a width of 6 and a height of 3, and this rectangle has 90-degree angles, so square corners. And so if I cut this rectangle and then rotate this piece up, so I have this side here and this side all in one line, I've opened it up. This angle, of course, the angle along a straight line is 180 degrees. It started out as 90 degrees, so I know that the two angles that are inside here are 90 degrees, so here I have a 90 degrees and here I have a 90 degrees, but the sum is 180. So I know by doing what I did that this angle here in between the two lines is 90 degrees. And that's what I'm going to call a perpendicular line, where I have a square corner essentially, a 90-degree corner. Okay, so let me look at the slopes of these two lines. So if I look at this line here, what's the slope of this? It's going to go down 3 and over 6. And so the slope of that is going to be -3 over 6, and I get my slope of -1/2. Now the line that I'm claiming is perpendicular to this is this line here, so I can calculate that slope as well. And what I'm going to do is I'm going to say, okay, the rise is 6 and the run is 3. Now notice I've kept my signs proper, because going down is going to be negative and going up is going to be positive. What the decline here, not the rise, but the decline is 3 and the run is 6, and here we have an increase of 6 with a run of 3. So when I simplify that, you'll see that I get 2 over 1. And so here's the relationship between perpendicular lines, is that their slopes are the negative reciprocals of each other. And so if I write that as a rule, I can say my perpendicular lines is the slope of one is the negative reciprocal of the other. It doesn't matter which line slope is which, it just has that relationship. Because if you solve now for M2, you'll find that M2 equals -1 over M1. That's just an easy swap. But that's the key thing about perpendicular lines. I don't expect that you necessarily be able to derive this, but hopefully it's convinced you that this is not just pulled out of the thin air, and that there is some, at least a graphical explanation of why this is so. Now, of course, if I change these dimensions, I still get the same thing. For example, if this was a 7, and I kept that as a 6, I would have -7/6, and this would be 6/7. And so you still have that same relationship. So even though I use numbers, this whole exercise was quite independent of numbers, so long as I kept my angle to be 90 degrees. Okay, so let me go back to this notion of slope as a rate of change. This is one of the fundamental concepts that we have in this particular course, a calculus course. One of the big questions in calculus is how fast. The other big question in calculus is how much. And so with linear equations, how fast is going to be the slope. So just to put an example around that, if we look at this change as being just a value a over b, we can think of the slope as for every increase in b units, there's an increase of a units. So here, remember, I'm keeping the independent variable x as the thing that I'm looking to change, and then there's a resulting change in a by this ratio. So in a little bit more tangible example, let's say at 1 p.m. I'm at 12 miles from home, and at 4 p.m. I'm 36 miles from home. So the calculus question in here is, how fast am I going? And so the first thing I do is I can say, okay, here I have my, my 2 points, 1 p.m., 12 miles, 4 p.m., 36 miles. So I can calculate my slope as just being the change in y divided by the change in x. Or in this case, we can call this variable d and this one t. So this is the change, this is d, the change in d over the change in t. But in any case, my division turns out to be 8, and so I'm traveling at 8 miles an hour. Now this isn't any great earth-shattering news, but there's a couple things to keep in mind here. When you have a linear model, translate your data points into ordered pairs like this, because once you have the ordered pairs, then all the procedures that we have around calculating the equations of lines and the slopes and things like that, fall into place. So kind of in the model of doing the word problems and multi-steps and organizing your data first, think in terms of your data as either values on a table or as ordered pairs, and that'll kind of lend itself to the computation procedures. Okay, so that's the slope. Let's look at the equations of lines and how we can get to that point. So for a line, m is constant, and we know from the definition that that's the change in y over the change in x. Now, if I choose any point x and y, and in fact generalize this, I get this same thing here where I have y, notice no subscript, minus y1, over x, no subscript, minus x1. So I'm suggesting here that x1 and y1 are known, and that x and y in the leading half of this is not known. We know that this is going to equal, these two are going to be equal, right? Because m doesn't change. And so when I rewrite this, what I can do is I can multiply here both sides by x minus x1. And so I have just on this side the y minus y1 remaining, and here I have the m times this unit, x minus x1. And so now here I have an equation for the line. I have it because I can determine the slope from 2 points, and then I go back to one of the points, and it doesn't matter which one I choose. It could be the second point as well. I can stick it in here and keep my x and y as variables. All of a sudden I have an equation. So I can get an equation of a line out of this by then rearranging the numbers if I wanted in slope-intercept form. So just a quick example here. So if I want to find the equation of the line through 1, 2, and 2, 5, the first thing I do is I calculate a slope. So this is 5 minus 2 over 2 minus 1 is 3. And then I'll take either point, and I'll take the first point, y minus 2 equals 3. And the crucial thing here is that you keep your parentheses straight here, that you put the parentheses around the x minus 1. It's not just 3x minus 1 here. It's going to be 3 times, in parentheses, x minus 1. And then we can extend the, we can expand that. Why do you suppose that worked like that? Okay, what was I saying? Oh yeah, we can get this form, multiply through the 3, through the parentheses, and then we can add 2 to both sides, and we get our equation y equals 3x plus 1. Okay, so let's make a substitution. Both of these points should work in this equation. So if x equals 1, we have 3 times 1 is 3 minus 1 is 2, and we get our y value, so that works. And if x equals 2, we have 3 times 2 is 6, minus 1 is 5, and there's the y value there. So that's the way to check. You just put the original points back into the equation, and it should all work out for you. Okay, so what we call that then is the point-slope form of the line. So The point slope form often is written where this is all combined into one, where you have y2 minus y1 over x2 minus x1 here. But I find it just as easy to write, what the definition of the slope is, and then have the differences between the y's and the x's there. And so this is known as the point slope form. So here's one for you to try. Find the equation of the line through these couple points here. So we have 6, 6, and negative 3, 0. So I'll give you a couple minutes to do that. Okay, so I did it that way, in fact. And we get the slope, and then we use the point. That's why it's called the point slope form. And so we get exactly the same thing. Now, if I use the other point, now here's where choosing one point is better than the other. You'll get exactly the same thing, but if you have one point that gives you where y equals 0, what that gives you is an easier thing to simplify, because the 0 drops out here, and all you have to do is extend the 2/3 over these parentheses, and you'll get exactly the same thing. So just as a kind of a little pointer, take advantage of the fact that you have some zeros in here, either in the way that the order that you set this up. Just make sure that the 6 and the 6 correspond, and the 0 and the negative 3 correspond. Here, putting the 0 here makes this simplification a lot easier. Okay, so here's another one. Give you a couple minutes to do this one. All right, so the first thing that you want to do is take the slope, and so we take the difference between the two y's and the difference between the two x's. And notice my parentheses here. If I did this without parentheses, I guarantee you about 20% of the time I'd make a sign mistake. So it's a little bit of just an exercise in accuracy for me. Okay, and then we'll put in the one of the points here, and just remember that this is the y value, and this is an x value, and it's x minus that x value, so we're good there. And then we extend that, and subtract 1 from both sides, and we get y equals negative 3x plus 2. Oops, that's not where I wanted to go. And then we can test it by, say, putting in this point here. If we have negative 3 times negative 2, we'll make 6, plus 2 is 8, so we get to our 8, and indeed we got the right answer there. Yes?
Do you need to use the point slope form, or can you just find the slope and plug it into y equals x?
Well, you can plug it in. Yes, you can do that. So essentially what you would do is calculate your minus 3, and you have y equals minus 3x plus b, and then put in your other point. Let's say negative 2 equals negative 3, whoops, this would be 8 equals negative 3 times negative 2 plus b, negative 8, and then here we have minus 6. Is that going to be a plus 6? This is a plus 8. Equals b, 2 equals b. In fact, maybe your text does it that way, or I know at least the calculus does it. Yeah, and that's perfectly good. And in fact, when you look at the arithmetic here, it's almost identical to what you're doing with this form. The reason why, with the fan going, it's doubly hard when you're talking, okay? The reason why I want you to use this form, or at least learn it, is because when we get into derivatives, and when you get into things like linear approximations, and some of these things that are involved in calculus that involve linearizations of things, this is going to be the more useful format. Okay, so if it's just a matter of finding the line, that's perfectly good, but make sure that you understand how to use the point slope formula. Okay, I'm not going to mark off because you're using the wrong method, okay, but you might find that this gets really difficult to think about when we're talking about linearizations, okay? Okay, so let's look at a couple other variations of problems involving lines, equations of lines. So let's say we want to find a line that's parallel to another line, and we know the equation of the line. This is actually a fairly straightforward kind of exercise because we know that m equals 5, right? We know just by looking at this form that we have a slope of 5. So all we have to do then is put this into our point slope form, drop in the 1 and the 7, and then by simplifying it we get y equals 5x plus 2. Now you know that this equation and this equation are parallel because they have the same slope, they have different intercepts, so they're not the same line. We can check that just by plugging in the point again, and we'll get y equals 7. Okay, so that's what you do with finding parallel lines. Now let's look at the slightly more complicated version. Let's say we want to find the line perpendicular now to a line that goes through 2 points, and it, yeah. Okay, we're good? Okay, so we want to find an equation of a line that's perpendicular to the line through 2 points, and we want that perpendicular line to go through this third point. Okay, so the first thing we'll do is we want to calculate the slope of the first line, and so we figure that is 9 minus negative 3 divided by 7 minus 1, and we get 12 over 6. So this line between these 2 points has a slope of 2. Now we could find the equation of the rest of the line, but that's not the question. We only need the slope, so I'll just stop talking about that first line and look at the second line, that we know that the slope of the line that goes through this point has to have a slope that's the negative reciprocal of this value here. So m2 equals negative 1/2, and then we just put our point in, y minus 3 equals negative 1/2 times x minus 2, and then we go through and simplify this. And so we have our equation. This is the line that's perpendicular to, that goes through this point, that's perpendicular through that line. And so let me just draw it out so you can visualize it. It's not important to graph it if you just need to find the equation, but it's nice sometimes to be able to visualize these things. So the first thing I'll do is I'll graph those 2 points, okay? And then I'll draw a line through them. And then this point is the point that we want to go through. Now if we calculate what that line is, we know that the y-intercept is going to be 4. So I'm going to just put the point there at 4. So I have 2 points. This is the point that I'm starting with. This is the point that continues the line. So when I draw a line here, hopefully from my sketch you can see that this is a perpendicular situation here. Okay? Everybody following? Okay, so let's talk about the 3 forms. I've, of course, mentioned 2, and they just are named after what you use. We have the slope-intercept form, so we have a slope and an intercept. We have the point-slope form, so we use the slope and a point to get to the line. Then we have this, what's called the standard form. Now the standard form will follow the standard form of a lot of equations, like a standard form for a conic section, like a parabola or an ellipse or a hyperbola. We'll put coefficients in front of x squared, y squared, xy, xy, and then a constant, and all equals 0. That's a standard form, just a uniform way to catalog what you have. We don't really use this form very much directly in linear equations, but the form that we do use is a form that's slightly modified from that. And let's say, the best way to show this is with an example. Let's say I have the line 3x plus 4y minus 12 equals 0. Now you know that's a line because you have both an x and a y in it, and there's no exponents other than a 1 for x and y. Okay, So the slight modification to this that makes this really useful, this form, and you'll often see equations written like this, is to be written like this. So the constant is on this side. So in linear algebra, this is a little bit more common form than the standard form. It's also a form that is really easy to graph. Okay, and the reason why is because we can make use of both of the intercepts. So the intercepts, the y-intercept is where x equals 0, right? So we have some value here. The x-intercept is where y equals 0, because then it's going to go through the x-axis. So to do this, if x is 0, we just have 4y equals 12. And so we just take y divided by 4 is 3. And so this is 3. And then if y is 0, it's just as easy. We just take 3x equals 12. And so then we know that y is 4. So these 2 points are really easy to graph. We'll say 1, 2, 3, 4. Here's 4 and 0. And this one is 1, 2, 3. 0, 3, and here's our line. So we've made use of both intercepts to draw the line. Now, so long as you're not down into really small values, this is a pretty easy way to do things, because just think about this, don't worry about it, and then just put your thumb over here and you say, oh, when x equals 0, y equals 3, when y equals 0, x equals 4. And so you have your 2 points that you can graph. And so graphing these kinds of an equation in this form is much faster than graphing the slope-intercept form. So if I were to put this into slope-intercept, I would have 4y equals minus 3x plus 12, and then I would divide by 4, and then 12 divided by 4 is 3. And so imagine graphing this. Okay, you know you start at 3, which we did, but then we have to go down 3 and over 4, down 3 and over 4. So we're at the same place. But I think this is faster, right? Especially when you put it in this form. This is not a unique form. In other words, I can multiply this by 2 and have 6x plus 8y equals 24. That'll be exactly the same line. This isn't unique, but this one is unique because y has a coefficient of 1 and that determines the coefficients of everything else. So it just makes it easy. You can make these equations generally with coefficients that are integers and not fractions. When they both have the same sign, you have a negative slope, you get used to that, but just don't underestimate the ease at which you can graph these kinds of equations. If you get into some type of financial work that involves linear programming, which is a branch of linear algebra where you're solving optimization problems, your equations will most likely come in that form. You'll find that they're easy to graph and easy to handle that way. So just know the names of these things. Okay, so the things that I want you to take away from this, the essential skills with the line. Now, you have absolutely zero chance of passing calculus without really thoroughly being adept with lines, okay? So, given 2 points, I want you to be able to calculate the slope, determine the line's equation. Given a line and a point, I want you to be able to determine a parallel line and a perpendicular line through a point. So given a graph, to be able to pick off 2 points and then make a line, okay, that's very similar to just this. It means you'll be able to read a graph. Given an equation in any form, you can modify it to a different form if you like, but I want you to be able to graph that. And so from an equation, be able to identify what the slope and the y-intercept is. And then lastly, write the equation of a vertical and horizontal line. So remember, y equals 4 is a horizontal line going through 4. X equals 2 is a vertical line going through the 2 on the x-axis. Fair enough? Okay? This is a definitive list of what you need to know about lines. Okay, so let's look at an application here. I think we have just enough time to do this. So here we have a situation where Bill's renting a car. He drove it 200 miles and paid $95. What I didn't write in here was assume that this is a one-day rental. Okay, Katie rented a car, drove it 150 miles and paid $85. The rental company charges a daily rate plus a per mile rate. What's the rate structure on this? So notice it doesn't say anything about lines or anything like that, but if the description of the rate structure is that you have a per mile rate, okay, that implies that that thing is constant, and then the daily rate, it has to do with some type of constant that gets added to it. So see if you can figure out what the rate structure is in the with this car rental company. Okay, so the difficulty of these kinds of problems is to decide, what kind of form the math that you're going to use takes, and what kind of form the answer takes in this. So, we're talking about lines, and so it should be obvious, not obvious, but it should be at least on topic that this is a linear. It's a linear problem. So we'll take this a step at a time and say, okay, the first thing I want to do is I want to make my data into coordinate pairs. And so what you do when you're using a rental car company is you drive a certain miles and then you get a charge out of it. So the independent variable is going to be the mileage. The dependent variable, which means what you're going to pay depends on how much you drive, so there's a way to look at that. So we have these 2 points, and so the task now is to find the equation of the line. So it's 85 minus 95 over 150 divided minus 200. And you could have done this the other way around, that's okay, but you'll end up with 10 over 50, which is 1/5, which works out to 20 cents a mile. Okay, so this is pretty good. This is a rate. That means when you drive a mile, you know it's going to cost you 20 cents. But then we find the complete equation, and we're going to say, okay, we'll put in one of the points. We'll choose this first one and say y minus 95 equals 0.2 times x minus 200. Multiply through the 0.2, and we get our equation. I guess I can let that go. Now, this equation is not the answer. Okay, that may make sense to you. It certainly should make sense to you because you set it up, but it won't make sense if somebody asks you what the rate structure is. You can't answer them y equals 0.2x plus 55. They'll kind of look at you funny. Okay, so what you need to do is it's an ordinary English question, answer it in ordinary English. The rental car company charges 20 cents a mile plus $55 per day. That everybody can understand. And without looking at your math, you think, okay, this is a reasonable answer to this question, and the answer is framed in the sense that whoever's asking the question can receive that answer and make heads or tails out of it. So one of the things I feel strongly about when you're doing word problems like this is always answering the question in plain English, just to avoid that translation. Your X may be my M, or not really M here, but maybe my T, and your Y may be my D, or something like that. You can have different variables in here, but the answer should, kind of make that transparent to the person asking the question.